Alrighty, I'm going to do a binary search. We're going to start with an array. I'll do an array of ints to begin with. Make an array with some random numbers in it. And we'll just write a function method to display the values. I used so I don't know exactly why they didn't do this. They didn't add a for each method to the array, but I should be able to do something like this, I would think. I could be wrong. That sucks. I don't know if there is a way to do it. I'm lazy. I want to do it the fancy way. Right? Far better than the way I was going to do it, which is for value they're the same thing. I don't know what it's unhappy about here. Apparently there's a singleton list. So those are equivalent. I'm going to do that because it's one line. Let's run it, and it should just print out our values. Well, that didn't do what I expected. That makes me sad. Interesting. I suspect it is the it's treating this as I'm going to go with this thing probably takes a yes. It's made a array of a list of array of ints. So this is one huge value in that. Oh, I can just do arrays.stream though. There we go. That's better. That's what I was looking for. But I still don't know why they just didn't add a for each to the array. This seems like overkill, but that's how you can do that. You can take your array and convert it to a stream. This should work now, I would think. There we go. Okay, so it's printing out our values. If we wanted to search the values for a number, well, let's go with that number. Pardon me. So here we're going to do the loop. Right, so we're going to go through each of the values, and we're going to say if the value equals the search value, we're going to break because we found it. And probably what we want to do is put in the int. So that's the index of where it was found. And I really need the value, right? So the problem with having done it this way, this kind of for loop, and this is rare, but it does happen. I really like using the for each loop. I use it almost all the time. Now I like using this for each loop, right? But here I want to break out early, so I can't use this one. The problem with using this particular one is I actually do care about the index, and there's no way to get the index. Some languages, when you do this kind of loop, they give you the value and the index. I know Python does that. And I want to say I think Swift does that, but I'm not 100% sure. For some reason, I do lots of loops in Swift. So I can't use this kind of loop. Or I can, but it becomes a little difficult. So I'm going to say final, or not final. So it is important that you do know all the different kinds of loops, because there are cases where it really matters. So what we're doing is we start off with the indexes -1. And then we're going to loop through the entire array. And if we find the value we're looking for, we're going to just remember where it was, and we're going to break out, and we're going to return the index. If we get all the way through the entire list without finding it, we're going to return -1. So this will return what index we're in. Right, so this should presumably, I don't think that this particular value is in that particular array, this should return -1. And it did, -1. And if we search again for the value 17, which is in our list, we get the value for, 17 was in there twice, so let's remove that one. That was a mistake. So it's the 11th, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? If I search for 10, it should return 0 because 10 is the first one. Let's say our array is really large. Let's say it's got 1 million items in it. There's this idea of this thing called big O notation. I'm not going to go into it in a lot of depth. You cover it in some other courses. If you take an algorithms course, it'll be in there. Maybe a discrete math course will cover it. So the big O notation for this algorithm is that we're going through from the beginning to the end, and it will search the entire array. Worst case, right? The worst case is it doesn't exist. So this is what's called an ON algorithm. It goes from the beginning of the thing all the way through the end, one at a time. That's ON, right? Because n is the length of the array. Right? So this could be 1, it could be 0, it could be 1 million, it could be 20 million, it could be 1 billion, right? So we would like to not do that. It's very expensive to search through an array that way, because it's got to loop through potentially 1 million times. So what we want to do is a binary search. A binary search cuts down the the searching in half every time. So it'll search the first half of the array or the second half of the array. And we'll go in, and then once you've narrowed it down to being the second half, it'll search the first half of the array or the second half of the array, the small array. And we've figured out it's here, we'll search here. And maybe we decide it's this one, we decide it's that one, or whatever, right? We'll go through that algorithm, but it reduces the, if you had 1,000,000 items, we look halfway through the list, and we can very quickly say it's in the first half of the array or in the last half of the array, meaning we can skip over the part that it's not in. For that to work, though, we have to sort the list, or the arrays. We can do that very easily, and won't make this final right now. Yeah, I'll do it this way. So we can just sort the arrays or the values by doing that. Oh, okay. It sorts it in place. Sometimes there might be a method called sorted. There isn't. There's parallel sort, which I'm going to guess, it's new to me. I'm going to guess that it is a faster sort for large items. Not going to worry about that. So all we have to do is say that we want it to sort it. Some languages will return a new sorted array and keep the initial array unsorted. In Java, what this method does is it sorts them in place. So that means that this array will actually go back to being final, will actually change now to be sorted. So let's see. And it is, right? 1, 2, 8, 10, 11, right? All the way up. And the index is changed because of where it's finding them now. So I'm gonna get rid of this right now. And we're just gonna call, actually I can keep one of them. So we're gonna change our search. It's no longer gonna be this way. So I have bad allergies today. So as I said, we want to cut the value in half. I'm going to do this recursively as well. Actually, we can do this way. So I didn't want to change the way this one worked, the search. So I'm making a new method, the binary search method, that's going to be recursive. And you'll notice the arguments are slightly different. So if we have our array, and let's change our array to be a little simpler, and I'll even keep it sorted. We'll just have 5 items. And the indexes are 0, 1, 2, 3, 4. So when I say the length, so that length equals 5, right? So 5 divided by 2 is 2.5. Java is either going to cut that down to 2 or round that up to 3. Now, I believe it's going to cut that down to 2. And we can check that. By just printing this out. So let's run that. And it did, cut it down to 2. right? There's our array. Our array, 1, 2, 3, 4, 5. The value cut in half, right? The middle index. And -1 is what we returned. So because that index is 2, we're now going to be looking at index 2, which is the value 3. And what we're going to say is, if it's greater than 3, now we only have to look at 4. If the value we're searching for is greater than 3, we only have to look at 4 and 5. If it's less than 3, we only have to look at 2 and 1. If it's equal to 3, we're done. So it's pretty simple to code. First off, we are going to say if, now we can get the int middle, final int middle value. And we get the middle index. If the middle value is less than the search value, we're going to do something. Otherwise, if it's greater than, otherwise it was equal to. And then we can return the middle index. Now, as you know, I only like having one return value, so I'm going to say final int index, and here I'm going to say, not that, I'm going to say return index here, and I'm going to say index is assigned that, and here I'm just going to say index is assigned -1. Apparently I can't type at all. And here I'm going to say index is assigned -1. And now we're going to search for 1. I'm not going to display the values anymore. I'm going to search for 1. We're going to search for 2, 3, 4, and 5. So it should print out -1, -1, 2, right? 3 is at position 2, -1 and -1. -1, -2, -1, -1. Cool. So all we have to do now is do a little bit of math. So our and we're going to call binary search. So actually we're going to say the index is assigned to binary search, passing in the values, and we're going to pass in the whole array. We're not going to try and make a small array. We'll just pass in middle index again for now. This is wrong. And the search value. And it'll be the same idea here, right? So this is math stuff. Right? We need to do some math stuff. So what is the math stuff? So the math stuff, which is not, it's a horrible name. I will change it. I'm going to put in 0 for now, just so we've got it, the right idea, and we'll talk it through. So we searched for 3, and we've passed in, or we've searched for 3, say, right? So we came in here. Let's actually bump this up. 6, 7. This now becomes 7. So we search first for 7 divided by 2 is 3.5, which gets it down to 3. So we're searching for 4 to begin with. Let's say we've passed in 6. So we're only going to look at 5, 6, 7 now, or index is 4, 5, 6. So the index we've got is 3, and we want to get to the index of 5. Okay. So we're here, and we want to get now to look at this, because we're cutting it in half, right? We cut this whole array in half, which means we split it down here, and we said, is it less than? We're going to look here. Is it greater than? We're going to look here. And if it is equal, well, we've got it. So we've got 3, we've got 7, and we want 5. So 7 minus 3 is 4. Divide that by 2 is 2. 3 plus 2 is 5. So that is the max, the array, the values, dot length, minus the middle value, middle index, right? So that is 7, and this is 3. Right? 7 and 3. We're going to take that, I'm going to divide it by 2. And we're going to add the middle index. So let's see if we just search. First off, the middle value is 4, so we'll try searching for 4, and it should hopefully come back with an index of something other than -1. It came back with 3. Good. Now we're going to search for 5. Sorry, we're going to search for 6. And hopefully my code's right, and it will return back 5. Nope. Did something wrong. I put that in the less than, didn't I? Yep. No, I put in the greater than. Okay, so debugging. We're going to print out what we're going to print out is the middle index and the value at the middle index. Right, so we're just going to print that out each time and see what's going on. And I didn't put in a new line, but it's, well, actually, we'll go ahead and do the new line. Print ln, not printf. My mistake. So 4, and then it's looking at 0. Why is it looking at 0? Right? Okay, so what's wrong with my math? Is it that we're coming in here? So let's put out a system out print line here of left, and we'll put one in here of right. We're going left. It means I just screwed up my comparison. So the middle value is 3. What I actually probably meant to do was this. It's completely arbitrary. I just goofed up on that. So let's see now what happens. There we go. So it worked, right? So our math was correct. So let's see if we were going the other way. It's going to be similar math. Except it's going to be not the length. It's going to be, so say we put in 2 now. We've got 3 and we've got 0. And so we just want to take the 3 and divide it by 2, which is 1.5, which will get us rounded down to 1. So all we have to do here is say that we want to take the middle index divided by 2. And we're going to search for, instead of 6 this time, we're going to search for 2, and hopefully it comes, 2, and hopefully it comes back with the number 1. And it did not. What? Went left, which is right, and I did the code in the wrong place. I'm not infallible, clearly. Run 6 again and just make sure it comes back with 5. Run 3 again, make sure it comes back with 2. Or, sorry, that was a mistake. Run 4 again and make sure it comes back with 3. And now we're going to pass in 2, which hopefully comes back with 1. There we go. So now let's search for 0 and see what happens. Didn't work. We'll come back to that in a second. So it worked. Oh, I was searching for 0 and it's not there. We'll deal with, I just want to deal with things that are in the list right now. So 1 returns 0. Okay. So let's do this. A reasonable chance of it working. 2, 3, 4, 5, 6, and 7. Now these should hopefully return the appropriate numbers 0 through 6. I can't tell because it's too noisy because of all my debug. So I'm just going to comment those out right now. This is one thing about recursion. It doesn't work, and then all of a sudden, boom, it works perfectly. Right? That's a very common thing. So it's working. Yay. We don't know if it's working for an array with an even number, though. So let's get rid of 7. And get rid of 7 from our search. And make sure this works as well. No, crash. Okay, so it's probably related to, so let's get rid of this. It's probably related to when we search for something that doesn't exist. Okay, so we'll fix that first. I'm going to put my prints back in because it won't be too noisy this time. And hopefully it helps us figure out what's going wrong. So what should be happening is we're looking at, oh, let me put back to a state that we know worked. So it should be looking at 4, then it should be looking at 2, then it should be looking at 1. Sorry, it should be looking at index 3, then 1, then 0. Because I am searching for 0, which is perpetually smaller than everything in the list. So it should be 4, 2, 1. Sorry, 3, 1, 0. And it was 3, and then it was 1, and now it's 0, and it gets stuck here because it keeps doing the same kind of thing. So that's odd. So that must mean, oh, I shouldn't have gotten rid of them. That it keeps going left. So it keeps saying that it's going left. So it's probably a simple thing of saying, if math stuff equals the middle index, index is assigned -1, else right, so basically we did the math stuff, we wound up with the same number, we're not looking anywhere different, so we're done, it's not there. So let's see if that works. Worked, return -1. I don't know why I kept doing print F, it should be print line. Got C on the brain apparently. Okay, and then the same thing's gonna happen with the other one. So now if we search for 8, same thing should happen. Return -1. So let's change this a little bit, just a little bit. We'll put in 10, 20, 30, 40, 50, 60, 70. We'll search for 60. It should return 5. And it did. Now let's search for 55. It should return -1. Blew up. But we have our print, so we can see what happened. So it got to the 40 and said go right. And it got to the... Okay, so there's one other test to put in here, that we have to say, or the math stuff, if we're going left, it's greater than the middle index. And this says, or the math stuff is less than the middle index. Did I get those backwards? Might have gotten those backwards. That's not right. So this is where we want to test things, right? So let's put in 10 and see if that works. Nope, that didn't work. So that change was not a good change. So my other thought is that this needs to be less than or equal to, and this needs to be greater than or equal to. And that seems to work. And now this is redundant because of the equality is already covered by the equals over here. So let's go back and put in, just to be sure, 10, 20, 30, 40, 50, 60, and 70. And let's comment out our debug statements. Okay, that worked. Now let's search for 0, which is not there and is before the beginning of the list. There, list of numbers. Let's search for 100, which is, or 1,000, which is after. Okay, and now let's search for 55, which is within the bounds, right? 10 through 70. Well, 55 appears in there, but it does not actually appear in the list. Still not working. So back to this. And I can even trim this down a little bit. I should be able to do this. And it's nice to get it to be a smaller set of values because you have less to read at this point in time. You want to narrow it down to a nice small test case, right? So let's go with 25. So rather than have to go through hundreds of values and all that and see what's going on, we can just see, okay, it went to 20, it went to 30, it went to 20, 30, 20, 30, right? Okay, so why is it doing that? So we went to 1, which is correct. So it looked at 20 and it said that we're looking for 25. It said that 25 is greater than, right? So the search value is 25, which means the search value is greater than the middle value. 25 is greater than 20, so it goes right. Let's print out with the math stuff. Oh, you don't have to use string format all the time. If you're just going to add to the end, then convenient to just do a plus. And we'll do the same with left, just so we've got it for consistency. But we will say left, and we'll put it in the right place. There. So I didn't get quite enough information actually. So I'm going to do the printf string.format. format. Math stuff, and I also need to know what the middle index is. Technically I didn't need that, but probably get rid of this one though. Yep. So we are saying which is one other change I could make to this. I could say middle index -1 divided by 2. And I could do the +1. So we're just going past the end of the array. Which is happening when it was going right. My mistake. So that probably means I want to say that here. Okay, and that means I probably want to do less than 0, right? So I don't want to go outside the array. Apparently that's already dealt with. So let's try printing out 10 and 20 and 30, and we won't have our prints. Zero, 1, and -1, so that's not quite working. Zero, 1, and 2, that works. And then we'll search for 11. We'll search for 21. Just want to see. And we'll search for 31. So outside the array works. And if we search for 0, or outside the min and the max, seems to work. Yeah. So it's only on the things that are in the middle. I'm actually going to punt on this. I'm going to point you at a much better solution than this one. So I was trying to approach this as a student would approach it, and just give you some little tips. The value of you watching me trying to decipher this any more than I already have is not, there is no value in it. But what I wanted to show you was that there's some strategies for doing this. I'm going to continue on with the other part I wanted to do, which was to make it generic. So again, this works fine as long as we're searching for something before, after, and it's not there, or one of the values that's in here. This code doesn't work right, and we know that. And like I said, there's a much better way to go about doing the binary search, and I will point you at what that is. I just wanted to come into this as a student and go, okay, well, this is the kind of stuff I might do to figure it out, to give you some techniques. So let's pretend this all works and go, okay, well, I don't want to do this I want to also do this for strings, right? I want to do A, B, and C, which means this now has to become a string. And this has to become a string. And we're also going to call display of the values. And maybe they're not sorted. Maybe it's CBA, so they'll sort afterwards. Of course, this doesn't work anymore because these are taking ints. So I'm going to make this a string. And I'm going to make this a string. And I'm going to make this down here a string. And this needs to be a string. Okay, problem. We can't do these comparisons with strings. This is what the compare to method is for, right? It's to take a string comparison and the search value has to be a string as well. So it's take an object, strings in this case, and convert that comparison to a number. So it's less than if this one is less than that one, I think. And we'll do the same thing here. And that's in the case that they're equal. So binary search, this takes a string as well. And we're searching for A. Right? So it's almost the same code, but not quite. But let's see if it works. So A is at 0. Let's actually change this to D, C, and B. So A should be -1. B should be 0. C should be 1. D should be 2. And E should be -1. And just to go way on a limb, Z should be -1. Awesome. Problem, we just broke it for ints because, ints aren't strings. So we could make it objects. We want to do that because then we lose all the type safety that we've just gained by having the strings and all that. So what we want to do is generics. So what we're going to say here is we're going to make this T extends comparable T. Right? We want it to be comparable because we want to be able to call that compare to method. And this just means that you can compare it itself, right? The string is comparable, a comparable string. Int is comparable to int. So we're no longer taking strings, we're taking t's, right? And we're going to do the same thing for this method down here, like that. And this isn't a string, this is now a t, and the value we're searching for is a t. And this is no longer a string, it's a t. And there we go, and this is no longer a string, this is a t, because it needs the same kind of thing, but it only needs a t this time because we don't care if it's comparable or not, right? We're just printing it out. So this now will let us do a system out print line on any kind of value. It doesn't matter what any array. Doesn't matter what the array is. So now let's run it and make sure that this still works. So we're going to put in A, which should be -1, B, which should be 0, C, which should be 1, D, which should be 2, and Z, which should be -1. And if we change this to integer, or ints, not sure if this will actually work without being integer in this particular case, but let's see. No, it's got to be integer. And here's the type safety, right? We're searching the values for Z, but it can't possibly be because we're dealing with integers. So 14 should be 0, 1, 2, 3, 4. Oh, it's sorted now. Sorry. 14 should be 0, 1, 2, 3, 4, 5, 6. Right? So it works. Might probably test more, but you get the idea. That's another example of using generics, right? So now we have a generic search. Now I'm going to tell you that this is all pointless. We shouldn't do this because what all we should do is this. Arrays binary search, pass in the values. And what we're looking for and run it. And that was 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. And if I search for 79 this time, it should be -1 because 79 isn't there. Yay. See, one line of code, right? I don't need to actually write a binary search at all, right? It's one line of code. So one really important lesson here is know your library because, almost every language is going to have something to do searching. And even better, I don't have to sort them. And we'll search for 15. minus 8. Let's search for 10 and just make sure that I'm not losing my mind. 0, 11, 1, 12. You said 14? 14 was it? 4. 15? I don't know where minus 8 come from. 15. 15 is minus 8. That's weird. 1. So I could be wrong. Maybe you do have to sort them in this case. I thought I remembered that it was... Okay, so it requires it to be sorted. I thought it sorted it before it did it, but it makes sense that it doesn't, because if you've already sorted it, you wouldn't want it to sort it again. It's an expensive operation. So sort probably does internally what's called a quick sort. It's a very good way of doing a sort. And the binary search does what I was trying to show you, but it does it properly. So I'm going to actually give you a link to... in the Learning Hub, I'm going to give a link to something that talks about how to do a binary search, but more importantly, it talks about a huge bug that was in binary search for decades. The math was a little bit wrong, and it only showed up when people started using it for very huge values. So you can see how binary search is properly implemented there, not this bad version here that doesn't actually work. But also realize that if you know the library, your life becomes so much simpler. So it's well worth looking at the library. The library is pretty big, but if you're going to be programming for any length of time, it's something you really want to get familiar with. So we've seen a little bit more on lambdas, more on generics, the concept of binary search, how to debug something, a bit more on recursion, and learning library. And that is it.